In this video, I'm going to give an introduction to using the Scikit-learn machine learning library for Python. Now, as the name suggests, the Scikit-learn library is a scientific library, and there's quite a lot that you can do with it. However, when you're getting started, it's very easy to either find some documentation that gets you very bogged down in mathematics, and then you don't really understand how to use the library or how to proceed on one hand, and on the other hand you'll find some documentation that will not really explain what you're doing to you, so you'll also kind of get bogged down because you'll not really understand how you're actually using the library and how the modules within the library work. So I'm going to try and explain some of the more commonly used estimators within the Scikit-learn library, but I'm going to restrict this video to kind of the basics. So we're going to look at machine learning, and we're going to look at supervised learning. So in supervised learning, the data consists of feature-target pairs that can be presented to the machine during the training phase. And in this case, I'm going to look at a classification problem. So the target data will be categorical, and the general problem is to identify or classify the target, which corresponds to a set of features where the target is unknown. Now, there are other types of problems which use regression, and in this case you're going to try and fit some sort of line or curve that is continuous, and then you're going to try and identify the target, the continuous target, at a set of features using the trend line or trend curve. And unsupervised machine learning is a bit more complicated. In this case, you essentially need to know your data a bit better, and then you need to make your own set of features up from the data and then feed this through to a machine as essentially a supervised learning program that the machine can understand. Before starting with the Scikit-learn library, you're going to need to make sure that you're proficient in using core Python, the numeric Python library NumPy, the Python and data analysis library Pandas, and the matplotlib plotting library. We're going to import these using their standard abbreviations. Now I'm going to create a nested numeric list and assign it to the object name data, and I'm going to create a list of strings and assign it to the object name columns. Now I'm going to call the DataFrame class from the Pandas library, and I'm going to use the two keyword input arguments, data and columns, and assign these to the objects that we just created. So let's save and run this script and examine our data frame. So our data frame consists of rows, which are index 0, 1 and 2, and these are known as observations. We have a number of columns which we call features, so we've got feature 1 and feature 2, and then we've got the target column of interest. Now, all of these are numeric, and the features can be grouped together collectively to make a matrix. This matrix is commonly called X, and X is capitalized because it's a matrix. So we're going to use the DataFrame method drop, and we're going to drop the target, select axis to be 1, and then we're going to use the method to NumPy to convert it to a NumPy array. For the target, because it's a vector, we're going to use lowercase y, and we're just going to select the column, and then we're going to use the method to NumPy to convert it to a NumPy array. And each observation in the matrix X corresponds to the observation in the vector Y. Okay, so now that we've got a general idea of how the example data looks like, we can have a look at using the Scikit-learn library. Now, instead of just going to the top and typing in import Scikit-learn as a two-letter abbreviation, what we tend to do is actually import each class from the Scikit-learn library individually. So the Scikit-learn library is grouped into modules. So if we type in from Scikit-learn import, we'll get a list of these modules. Now we don't normally just import the modules, we import a class from the module. So in other words, what we type in is from Scikit-learn.module import and then our custom class or our custom function. Now custom classes will use camel case capitalization and functions will use all lowercase with an underscore as a separator. So let's have a look at an example. Let's use the neighbors module. So the module is called neighbors and we're going to import, and here we can see kneighbors classifier is a class and has camel case capitalization, and kneighbors graph is a function and is in all lowercase using an underscore to separate the two words. So once we've imported a class, the next thing we need to do is instantiate the class. So this means create an instance of a class and assign it to an object name. Now most of these classes have keyword input arguments, and the keyword input argument will be class specific. However, the point I want to make here is that a keyword input argument has a default value, and if we don't provide the keyword input argument, the default value will be taken. So once we've created an instance of a class and assigned it to an object name, we can call the object name and then type in a dot and then access a number of methods. We can use the method fit and provide the positional input arguments X and Y. Now the method fit occurs in place, so it doesn't have any return statement, so we don't need to assign it to an output. Once we've used the method fit, we can use the method predict, and predict takes an input argument which has the same number of features as the X data, but can have a different number of observations. Now this has a return statement, and this will be the predicted target data, so we can assign this to a new variable name y2 or y2 predict. So the general form for this type of class, called an estimator class, is from Scikit-learn.module import estimator class, instantiate a class by assigning it to an object name, then calling the method fit, providing the X and Y as keyword input arguments, using the method predict, providing a new matrix X2 which has the same number of features as X, and getting the target Y2. There's a similar type of class called a transformer class, and transformer classes are normally used when pre-processing data, so they'll be used directly on either the target or the features directly. So instead of using X and Y in the fit, you're going to either just transform X directly or transform Y directly. So in this case, we'll transform X, And then instead of using the method predict, you'll use the method transform. Now, because the method fit and the method transform have the same input argument, they can be combined into the method fit transform. There's another type of class called a predictor class, and instead of just giving you a direct value, it will give you a probability. So once again, it has the method fit, but instead of using the method predict, the method predict proba predicts a probability. And finally, there's a type of class called a model class. Now, a model can just be thought of as a series of estimators, and each estimator will have a score, and typically the estimator with the highest score or the best score will be used to predict new values. So the above lines of code show basically the general template for using the Scikit-learn library. So first of all, we import the class from its module, then we instantiate the class, and then we call the appropriate method. The Scikit-learn library has a number of example datasets within the datasets module. So we need to type in from scikit-learn.datasets import, and then we've got a number of load functions to import different datasets. Let's look at the iris dataset, which is commonly used as an example dataset for machine learning. So let's just call the function and assign the output to iris. This gives us a bunch file which can essentially be accessed as a dictionary. So let's look at the description. So we've got 150 observations. We've got 4 features, and these are basically the lengths and widths of the petal and sepal of the plant. And these are all present within the numeric matrix called data. And we've got the target vector. So this is our capital X and small y respectively. And we'll see that the target has labels 0, 1 and 2, and that's because there's 3 different target names, and these are encoded as numeric values 0, 1 and 2 respectively. So just to understand this data a bit better, what we're going to do is convert it to a data frame. So let's type in iris and then access data using the key data and assign it to the object name data. Now we want to get the columns, and we can access these by using the key feature names, and we can assign this to columns. Now we can create a data frame using the data and columns. So this data frame doesn't contain the target data, so let's go ahead and create a new column within the data frame called target. And then for the value, we'll use the bunch file alongside the key target. We'll want to change this column to be of the type category. So we'll use the method as type and the string category. So if we have a look at our data frame now, we'll see that the target is numeric. Now let's go ahead and replace this with the target names. So I want to create a dictionary which gives the numeric value of the target names as the key and gives the value of the target names as the value. So for this, I'm going to need to know the length of the list of target names, and then I'm going to create an empty dictionary, and then I'm going to create a for loop, which is going to basically add each index to the empty dictionary and assign it the corresponding value. So let's run this, and I've just noticed I've made a small mistake. That should be I and not N. Okay, so we have the strings within the dictionary. And now we can use this dictionary to basically update all the values within the column target within the data frame. So we can use the attribute cat, and then we can use the method rename categories, and then provide the dictionary as the input argument. And I've just made a small mistake. I've added an underscore, so let me get rid of that. So this may be similar to the type of data that you'll start with. Let's actually just save it to Excel, and we can open up the Excel spreadsheet. So the Excel spreadsheet is perhaps similar to the way the data would have been originally recorded. So let's just have a look at it, and just to clarify, what we see is 4 features, and then we have numeric values for all of these features, and we can create the matrix X. Now the target data in this case is categorical, and we would need to change this to be numeric before we assign it to the vector Y. And we've got 150 observations because we're starting from 0, so we're using 0 order indexing. Now that we have the data in the form of a data frame, we can use the Seaborn library to create a plot so we can visualize the data. So let's import Seaborn as SNS, and then we can use the pair plot function to create a pair plot. So the data is just going to be the data frame, and then I'll supply the keyword input argument hue, and I'll assign this to target. So it will select each category in the target column and use this for the color. So I get an error because it's trying to rewrite to the Excel file that's open in Excel. So let's comment out that line of code and run it again. Right, so visually what we're trying to determine is how well separated are the blue, red and green data points. So the diagonal shows 1 feature, and each of the other plots shows 2 features. So you'll see if we look at the diagonal that in the third plot, the blue data is well separated from the red and the green. However, in the earlier plots, they're all kind of mangled together and hard to separate. Okay, so if we look at the plots in 2D, we can see that the blue data points are well distinguished from the red and the green. We see, however, in some of the plots that the red and the green data points are essentially overlapping, so it's hard to define a boundary between either data set. However, in some of the other data sets, we can see that the red and the green data points seem to be separated, and we can visually see a boundary using our eyes. So if we look at this plot in 2D and the plot in 1D below it, we can see that we get more information. So now the next logical question is, what do plots look like in 3D? So let's import Axis 3D and create a 3D scatter plot. So let's base it on the scatter plot, which was well separated in 2D. And let's see if we can separate the data out a bit better by adding a third dimension. So we're going to plot petal length on X, petal width on Y, and sepal length on Z. And we're going to use conditional logic to plot the data points that are setosa in blue, versicolor in red, and virginica in green. And now let's just add the axis labels. And let's have a look at the 3D plot. So here's the 2D scatter plot. And what we're interested in is how well can we separate out the red and the green. And you can see that we can visualize the boundary in just a bit more detail in 3 dimensions. Now our data has 4 features and we only use 3 features to create this 3-dimensional plot. So theoretically we could create a 4-dimensional plot and use the additional dimension to further distinguish the green and the red boundary. Now as humans we can only visualize data in 3 dimensions. However, mathematically we can use the 4th dimension and even higher dimensions and use this additional information to better separate out, in this case, the 3 species. Okay, so now let's open up the data frame and suppose we want to work backwards now and we want to get the matrix X from the data frame and the vector Y. We'll note that Y is categorical and it's got 3 different strings. So we need Y to be numeric categories, 0, 1 and 2 respectively. So in order to do this, we can use the label encoder transformer class found within the pre-processing module. So we'll need to import the class from the module. Then we'll need to instantiate the class and assign it to an object name. So we'll assign it to LE in this case. And then we need to fit the data to be transformed, which is going to be the original Y data, which is within this data frame. So it's iris_df, and then it's the column target. And then we can use the method transform and we'll assign the result to a new object Y. So transform uses the same input argument as fit, so it's going to be iris_df and then the column target. And recall that for a transformer class we can combine fit and transform together and use the method fit transform. Okay, so in our case we also want to get the matrix X and we're just going to select iris_df and drop the column target. So the axis is going to be 1 and then we want to use the method toNumPy to convert it to a NumPy array. And that gives us the NumPy array X. Note that all the dimensions are measured in centimeters, which makes sense to us because we can measure the dimensions of the plant in centimeters. However, it doesn't really tell us what feature is better than the other features, and it is common to use a so-called standard scalar. So when we use a standard scalar, we set each feature to have a mean of 0 and a standard deviation of 1. And with these dimensionless units, we can compare the difference of each feature with respect to the other features. So the standard scalar transformer class is found within the pre-processing module. And once again, we'll need to import it and then instantiate it. And in this case, we'll leave all the keyboard input arguments at their default values. And we can go ahead and use the fit transform method. So this time the input's going to be x, and we'll assign the output to x2. And both of these are matrices, so they're going to have a capital. So we can have a look at x2 within the variable explorer. And we can open it up side by side with the original data. So it's kind of hard to see how these relate to one another, just in table format. So we'll go ahead and plot this again. So let's uncomment out this plot and let's copy and paste the code. And instead of plotting from iris_df, we'll plot from x2. And this is going to be the second column where y is 0. And then it's going to be the third column where y is 0. And then it's going to be the 0th column where y is 0. And it's from x2. And the unit's obviously not in centimeters anymore. So that's y equals 1 and y equals 2. So we can open the two plots up side by side and we can see the standard scale. So if we expand this to take up the full screen, we can see that the blue data points in terms of pedal length are a full standard deviation away from the other data points. So clearly well separated. Our data has 4 features as mentioned earlier, and we essentially just threw a feature away when creating this 3D plot. It is instead quite common to perform some sort of dimensionality reduction transformation, and one of the most common ones is PCA, or Principal Component Analysis. So we're going to import the PCA class from the decomposition module, and then we're going to instantiate it, and we're going to use the keyboard input argument number of components and set it to 3. And now that the transformer class has been instantiated, we're going to call the method fitTransform, and we'll input the original data x and we'll output to x3. So now we'll just copy and paste the code to plot, and we'll just modify to plot x3. And this is going to be the new feature 0, feature 1, and feature 2. So let's change this to be figure 4. And we want to plot x3 and not x2. Let's also change the number of components to 2, and we'll create a 2D scatter plot. So let's change x3 to x4. And let's get rid of z. And let's also change the projection because it isn't going to be 3D. Okay, so let's run this code, and to the left hand side let's move the 3D plot that was done with the standard scalar and compare it to the PCA plot. So what we see with the PCA plot is that feature 0 has the highest variance, and actually you can almost distinguish all the species just using the new feature 0. So let's compare this 3D plot with the 2D equivalent. So the most variance is on feature 0, and then there's some slight variance on the new feature 1, and then there's an even smaller slight variance on feature 2. Let's also plot it with just one component. So this will give us only one axis. So instead of plotting x and y, we're going to just plot x, and we're going to set y to be numpy.zeros. And because we've got 50 of each data point, we'll send it to numpy.zeros with 50 as the input argument. So let's go ahead and have a look at this plot. So as expected, the red and green overlap slightly. And just so we can see the overlap in a bit more detail, I'm just going to change the y-axis to be what the numeric value for the target is. And here you can see where the red and the green overlap. Okay, so now I'm going to copy and paste the code that I used for the PCA and the PCA plots. And instead of using PCA, we're going to use another transformer class. So this is from the module manifold, and we're going to use Isomap. So it's also got a keyword input argument in components, and we'll set this to 3. Okay, so I'll just quickly speed up the recording where I'm modifying the code to create a new figure and moving to 2 dimensions and 1 dimension respectively. So let's now go ahead and run this code. So the Isomap is a non-linear transformation, and as you can see, it's stretched the data out, so you can see the red data points, the green data points, and the blue data point. And we can clearly distinguish the 3 features using the Isomap. Okay, so that's us done some initial visualizations. And now what I'm going to do is restart the kernel and just simplify my code a little. So we need numpy, pandas, matplotlib.pyplot as PLT. We want the 3D axis as well. And this time I'm just going to get the target matrix capital X directly from the iris bunch. So recall that it's a dictionary and we can access this using the key data. Likewise, I'll get the target vector y, lowercase y, directly from iris, and we'll access this using the key target. So next, I'm going to use PCA to get transformed data with 2 components. And then to simplify, I'm going to take every 10 data points. So let me just save this new script and run it. Okay, so we can see our simplified matrix x3 and our target vector y3. And I'm going to use this simplified dataset to explain how some of the commonly used estimators within the Scikit-learn library work. So let's plot this data out. And to this dataset, I'm going to add 2 additional data points. So I'm actually going to take them from x2. So x2 is the data, the full data set that's went through the 2-component PCA. So I'm going to take point 33 and I'm going to take point 133 and I'm going to color them in black and magenta respectively. Now we know from the dataset that these correspond to classification 0 and classification 3 respectively. However, for this discussion, we're going to consider them as unknown data points. So how do we classify these unknown data points using our existing data? Well, let's look at nearest neighbors. So the nearest neighbor to the black point is this blue data point. So we would guess that the black data point is blue. Now, using just the closest nearest point gives a vague kind of estimate. So we may want to use the nearest 3, the nearest 4, or nearest 5, and they are all blue. So we would be pretty certain that the black data point is blue. Now, on the other hand, if we look at the magenta data point, the nearest point is red, and then the second nearest is green, and then the third nearest is red, and then the fourth nearest is green. And then eventually when we look at 5 data points, we see that it is closer to the green than it is to the reds. So this is the concept behind k-nearest neighbors, which we'll now move on to. So to use k-nearest neighbors, what we need to do is import the k-nearest neighbors class from the module called neighbors. Then we need to instantiate it. So let's call the class. And here we see we've got a number of keyword input arguments. And I'm going to change the neighbors input argument. It has a default value of 5 and I'll change this to 1. And now I can use the method fit. And I can fit, in this case I want to fit the x3 and y3 data. And the fit method is in place, so it doesn't have an output. Now let's create new data points. So let's create the array x4 that has the same number of features as x3. And although these data points are known, they weren't used to train this estimator. So we'll use them as unknown data points. And we'll try and predict their values using the method predict. Okay, so let's open up the new matrix x4. We see it's got the same number of features as the original matrix x3, but it has a different number of observations. And our predicted value of y4 shows 0 and 1. And recall that 0 is blue, 1 is red, and 2 is green. So let's update the number of neighbors used in the estimator to 2. and we get the same result, 0 and 1. So for the black data point, it's pretty obvious that it's 0, but for the magenta data point, we see that the nearest neighbor was red and the second nearest one was green. But because the nearest one was red, we kept it at the prediction 1 red. However, if we change the nearest neighbors to the 5 closest nearest neighbors, then we've got 4 nearest green neighbors and 1 nearest red neighbor. So the prediction is updated to 2, which is green. Okay, so we've created 2 k nearest neighbors estimators, one using n neighbors equals 1 and the other using n neighbors equals 5. And they gave different results for a data point. So the question is, what one of these estimators is correct? And the answer here is that we don't know because we haven't done any testing and we've no data which evaluates how accurate each model is. So to get around this, what we're going to do is reserve some of our data for testing. So we're going to import the train test split function from the model selection module, and we're going to supply x3 and y3 as the x matrix and y vector, and these are the positional input arguments, and we'll assign the output of the function to the object name split data. So note that split data is a list and it has 4 elements. So we essentially see that the data has been randomized and that some of the observations are split. So we've got x3 training, then we've got x3 test, then we've got y3 train, and then y3 test. And so to the left hand side, instead of specifying a single object name, we can specify a list of object names, which is the length of this list. So every item in the list will be assigned to the respective object name. Now we can have a look at the optional keyword input arguments to this function. And to get some more detailed documentation, I'm just going to highlight the function name and press Ctrl and I to inspect it, and the information will be opened up in the help pane. So I'm going to use the keyword input arguments test size and train size. So I'll set them to 0.25 and 0.75 respectively. Now these should sum up to 1. Now it means 25% of the values will be used for testing and the other 75% will be used for training. And we've seen that the split data was randomized in comparison to our starting data. So behind the scenes there's a random number generator, and we can set the seed of this random number generator using an integer value. So let's set the random state to equal 1. And let's just open the 4 values. So we've got the x3 train, the x3 test, the y3 train, and the y3 test. In Python, it's also possible to assign the return statement of a function to multiple object names by just using commas. So we don't need to explicitly specify the left hand side as a list. However, you may prefer to do so just because it's easier to understand the code. Now, if we change the random state from 1 to 2, we see that we get a different training set and a different test set. If we return it back to 1, then we get the same training and test set as before. So that's just a consequence of setting the random seed, and it works as expected. Okay, so it's worth just visualizing on a plot how the training and test dataset look. So let's just copy the code from earlier. And now we just need to change x3 to x3 train and y3 to y3 train. And this will give us a plot of the training data. And let's just update this to figure 2. And now we just want to add the test data. And the concept behind the train test split is that we train an estimator using the training data, and then we test the estimator using the test data. Now the estimator will not know the actual y3 test values of the test data. So just to demonstrate the data from the perspective of the estimator, we'll color code the unknown data points in black. And we can use this to visualize the two random states, random state 1 and random state 2. Okay, so what I'm going to do is copy and paste the code where we use the KNN estimator class. And I'm going to update the fit to use the training data, and then update the predict to use the test data. So let's go ahead and run this. And I get a value error. And this is because I've used the test and training data in the wrong place. So I want to perform the fit with the training data and the predict with the test data. So let me go ahead and rectify this. And let's have a look at the original x3 test and y3 test data and compare y3 test to y3 predict. So we see that we've got two black data points which have been correctly identified as blue. So that's the 0, 0 and 0, 0. And we've got two red data points that are correctly identified as red. So that's 1, 1 and 1, 1. So in this case, all the test data points have been identified correctly. Now we can have a look at some evaluation metrics. So from the metrics module, I'm going to import the accuracy score, and I'm going to use the accuracy score function to calculate the accuracy score. So the input arguments will be y3 test and y3 predict, and it's basically going to calculate the ratio of correct values. So in this case, we've seen that the 4 test data points were given the right classification, so we expect this to be 1. And we're also going to have a confusion matrix. So the row index of the confusion matrix corresponds to the values in y3 test, and the column index of the confusion matrix corresponds to the values of y3 predict. So in this case, we see 2 and 2 across the diagonal. So in y3 test, we've had a 0 value and a 0 prediction, and this occurs twice, so that's why 2 is there. Likewise, we've had a test value of 1 that's been correctly predicted as 1, and this has occurred twice. Now this confusion matrix should be 3 by 3, but because there's not been index 2 in either the test or prediction, it's not showing up in this case. So let's change the random state from 1 to 2 and rerun this. And we see that the accuracy score has went down from 1 to 0.75. So that means 3 out of 4 predictions are correct. So let's open up y3 test and Y3 predict. And so we see that one of the values is supposed to be classification 1, but it was misclassified as classification 2. So if we have a look at the confusion matrix, we see that not every single value is along the diagonal this time, and this is a consequence of having a misclassification. So non-diagonal values are misclassifications. So we see we've got the value 2, and our 2 black data points that were blue have been correctly predicted as blue. So this corresponds to 0, 0. And because this occurs twice, we get the value 2 in the top left corner of the confusion matrix. So the first row of the confusion matrix is 2, 0, 0. So we've got 2 original blue test values that were correctly identified as blue. 0 of the original blue values were incorrectly identified as red, and 0 of the blue values were incorrectly identified as green. Next, we see that our red data point was incorrectly identified as green. So this means the first row of the confusion matrix is 0. 0 red points incorrectly identified as blue. 0. 0 red points correctly identified as red. And 1. 1 red point incorrectly identified as green. And the final row of the confusion matrix is 0, 0, 1. 0 green points incorrectly identified as blue, 0 green points incorrectly identified as red, and 1 green point correctly identified as green. Okay, so just to recap here, we are calculating the accuracy score, and we want to calculate the accuracy score to determine which estimator is the best. Now, to calculate the accuracy score, we need to use the train test split, and the train test split has a random element to it. And as you've seen, when we changed the random value from 1 to 2, the accuracy score dropped from 1 to 0.75. So as a result, the accuracy score has a high variance. So this makes it a bit problematic to determine which estimator is the best. And this high variance is partly due to the low number of data points used. Remember, we used every 10th data point, so let's use the full set of data points and rerun the code. Here we see we've got an accuracy score of 1, and all values lie on the diagonal. So that was with a random state of 2, so let's change this to 1 and compare. So we've still got an accuracy score of 1, so the confusion matrix remains the same. And now let's change it to the random state of 3. And we see that we've got 2 incorrect classifications. So the accuracy score is 0.947. Okay, so we performed an accuracy score on our model, and this is known as a validation. However, we've seen that this validation has a high variance, and so it makes it difficult to compare the accuracy score from one estimator to another estimator due to the high variance. So in order to overcome this, we instead use cross-validation. So the following schematic denotes tenfold cross-validation. So what we are doing here is we are taking 10% of our data, which is the red square, and using this 10% of data for testing. We're going to train the model using the existing 90%, and this will give us an accuracy score. So once we've done this, we're going to then take the next 10% of the data and use this for testing and use the remaining 90% of the data for training. And this will give us another accuracy score. And we'll basically repeat this until we've used all the data once for the sake of testing. So this will give us 10 different accuracy scores, and we can take the mean of this accuracy score. And because we've used all the data for the sake of testing once, and the fact that we've got 10 different measurements and taking the mean of it, the variance is substantially reduced, and as a result we can use this cross-validated accuracy score mean to compare different estimators to one another. So to compute the cross-validation score, we're going to use the cross-val score function from the model selection module of Scikit-learn. So we'll need to import this function, and then we're going to assign the output to CV score, and we'll call this function. And let's just comment out the lines of code that we don't need to use anymore. So for the estimator, we only need to import it from its module and then create an instance of it. We don't need to call the methods fit or predict. So we supply the estimator as the first positional input argument, and then the x3 and y3 data. We can provide optional keyword input arguments such as CV equals 10, so that means we'll perform a 10-fold cross-validation. And we need to set the scoring to equal accuracy. So we use the string accuracy, and it will compute the accuracy for each of the 10 folds. So we get the results as a NumPy array. So 1.933, 1, 1.866, 0.933, 0.933, 0.933, 1 and 1. So we can calculate the mean and the standard deviation. Let me just rename these CV score standard deviation and CV score mean. So here we have the score of 0.960 and the standard deviation of 0.044. And we can go ahead and change the number of nearest neighbors in the nearest neighbors classifier. So we changed it from 1 to 5. Let's try 10, 20, 30, 40, and we see the scores beginning to fall because the models get more rigid and we're performing some misclassifications. So we use the function cross-validation score to calculate the cross-validation of a single estimator. Now we're going to look at creating a model, and a model can be thought of as a series of estimators. To do this, we're going to use the model class GridSearchCV, and this is found within the model selection module. So once again, we need to instantiate it. So we see the first positional input argument is the estimator, and then we've got this thing called parameter grid, which we'll get back to in a second. And then we've got scoring, which we want to be the string accuracy. And we want to perform 10-fold cross-validation, so we'll set CV to equal 10. Now let's go back to our estimator. When we initiate it, we can optionally set a number of keyword input arguments, and these all have a default value. So we can specify a single one of these, or in the case of creating a model, we can create this parameter grid, which is a dictionary. So the key of the dictionary is going to be the name of the keyword input argument for the estimator. And the value is going to be all the values that we increment. So it's going to have the form of a list or a NumPy array. So let's use the function aRange to start from 1, to stop at 31, and to go up in steps of 1. So with the grid search CV class, we're essentially going to create 30 different estimators, and each are going to have a different value of n neighbors. Now, the model has the method fit. Now, fit will fit the data to every single estimator within the model. The model also has the method predict. So since we've used scoring accuracy, the model, when we use the method predict, will use the estimator that has the highest score, i.e. the score closest to 1. So bear in mind we would use predict on a new set of observations where we know the features and we want to determine the target. Just for convenience, we'll just use the data we started out with just to demonstrate that predict works in the same manner as a single estimator, because it is using a single estimator, i.e. the estimator with the best score. Okay, so model KNN has a number of attributes, and these attributes unfortunately end with an underscore, so aren't listed when we type in the dot and tab within the script. However, if we do it within the console, they are listed. So I'm going to use a number of these attributes to get the cross-validation results, the best score, the best parameters, and the best estimator. And I'll assign all of these to object names so we can view them within the variable explorer. So first of all, let's have a look at CV results. So CV results is a dictionary, and we can see that the size of most of the values is 30, and that's because there's 30 different estimators. So we've got 30 different scores for each of the 10 folds. So we can have a look at all the parameters used, and then we can have a look at the mean test score and the standard deviation of the test score. And we see that we have the best parameters, so it was number of neighbors is equal to 3, and the best score is 0.967. And we also see that we've got the best estimator, and it's a k neighbors classifier. So this is just equivalent to creating an estimator where the number of neighbors is equal to 3. So now what I want to do is add another parameter to the parameter grid. So I'm going to add the keyword input argument weight, and I'm going to assign it to a list, uniform, and distance. So during the cross-validation, we'll take into account the distance away from the test data point that each neighbor is. And when we do this, we see that we've got a new higher best score, and the number of neighbors is 8, and that distance works slightly better than uniform. And if we look at the parameters that we went through 60 values. So the grid search CV can be used to find the best estimator that gives the highest score. However, if there's a lot of parameters in the parameter grid, and if the data being analyzed is large, then it's going to take a very long time indeed. So there's a similar class called Randomized Search CV, and you'll see that most of the keyword input arguments are identical. So there is a slight difference. Instead of parameter grid, we've got parameter distribution, and this just highlights the fact that this class will go through the values in the dictionary randomly instead of going through them in a grid-like pattern. We also need to specify the number of iterations because we're going to go through a smaller number of iterations and we're going to go through them randomly, and we're going to try and get the highest score. So in this case, the highest score is 0.967, which is just slightly lower than the highest score seen with the grid search, which was 0.973. And as I mentioned, this runs a lot faster because we're not going through every single value. So this may be important if you've got a very large data set, or if you're going through a lot more parameters. So the slight difference that you get between the two classes of model may not be significant enough to warrant going through the procedure. That's a lot more time consuming. So if I up the number of iterations from 10 to 20, you'll not notice any difference in the best score. We still get 0.967. If I go from 20 to 30, then I'm going to get the higher best score, which is 0.973, which is the same result as the grid search CV. So far, we've looked at using k-nearest neighbors and looked at how we can use more features to better distinguish different classifications. Now, there is a drawback when using multiple features, and the problem is that we need enough data to adequately cover each feature. So say we've got one feature and we'll use an X to denote a data point. Then in this case, we'll uniformly spread the data points out, and we want the data points to be spread across the entire feature. Now if we go from 1 to 2 dimensions, then we're going to need to have the number of data points to the power of 2. And if we go to 3 dimensions, then it's going to be to the power of 3. And if we go to n dimensions, then it's going to be to the power n. So in order to use k-nearest neighbors, we need the data point under investigation to be near an existing data point or multiple existing data points, i.e. the nearest neighbors. And in a multi-dimensional space, we get more and more data hungry. And if we don't have enough data to sufficiently cover all the dimensions, then k-nearest neighbors becomes less useful. So we need to think of other estimators which we can use to cover more complicated situations. So we've seen that our training data consisted of a number of discrete data points, discrete both in the feature space and also discrete values. Now some of the approaches to a classification problem are to instead use the training data to create a model that is continuous across the feature space, so we can use it to estimate the classification of any unknown set of features. And if we begin with some naive assumptions, we can use the Bayes theorem. And the Bayes theorem states that the probability of y given x multiplied by the probability of x is equal to the probability of x given y times the probability of y. So in other words, the probability of going out because it is sunny multiplied by the probability that it is sunny is equal to the probability that it is sunny because you are out multiplied by the probability that you are out. So in our classification problem, we are interested in y given the features x, So we can divide through to get the probability of y given x is equal to the probability of x given y multiplied by the probability of y divided by the probability of x. And we can assume that each feature gives an independent and equal contribution to the outcome. So if we assume that we've got two features for simplicity, then capital X equals small x1, comma small x2. So the small x's denote vectors, and we can separate these out. And since we are assuming that we've got continuous data, we can typically assume that the data is distributed using a normal or Gaussian distribution. Okay, so I'm just going to highlight the previous code and press Ctrl and 1 to comment it out. Now, we looked at creating an estimator and using it to perform a fit and predict. Then we looked at evaluation metrics, then we looked at cross-validation, and then we looked at cross-validation with a change in parameters. So I'm just going to copy and paste the code again, and I'm going to have a look at the naive Bayes estimator class. So let me just copy these two lines so we can see it in comparison to the k-neighbors classifier. So recall, we imported the class from the module, we created an instance of the class, and then we could use the fit and predict methods. So that should be y3 there. So instead of using the neighbors module, we're going to use the naive Bayes module, and we're going to import the Gaussian NB class, Gaussian naive Bayes class. So let's create an instance of it. Let's instantiate the class. And then here you see a similarity between this estimator and the previously used estimator. And you see that this new estimator has the method fit and predict. Now, instead of doing this, we're going to use the cross-validation score. And recall that the first input argument was the estimator. So we'll just replace KNN with Gaussian NB. And now we'll restart the kernel and run the code. So this will perform the cross-validation. And what we're interested in is the cross-validation score mean. And we see that this is 0.9. So this is lower than what we got when we used k-nearest neighbors. So it means this is a worse estimator than k-nearest neighbors for this particular data set. So we'll move on to look at another type of estimator. Okay, so we can have a look at another estimator. That's a decision tree. So a decision tree essentially asks a question about one of the features. Now recall that the features are numeric, so the question is basically going to be, are the features above or below a certain value? Now to illustrate this, we're just going to take every 10 data points and we're only going to look at the red and the green features. And then we can ask a question about feature 0. So we're going to split the data along feature 0. So anything below the point 0, which we'll pick in this case, will be split to the left, and anything above the point 0 will be split to the right. So then we will want to compute a metric which tells us how well the line split our data. So we compute a thing called the Gini, and here we see we've got 2 red points and 0 green points on the left hand side, and we've got 3 red points and 5 green points on the right hand side. And we can use these to calculate the Gini. So on the left hand side we get a Gini of 0, and on the right hand side we get a Gini of 0.79, which gives a total Gini of 0.632. Now we can conceptualize using a for loop to calculate the Gini as we go along feature 0, for example in steps of 0.1. And if the data is perfectly split, we'll get a Gini of 0. So if we have a look at the chart, we can see that this is about 1.25. So let's change the line to there. Actually, it's a bit over, so let's change the line to 1.5. And now we can calculate the Gini, and the Gini is 0. So the data shown is quite simple, but the general point of the decision tree is that we'll ask a question about feature 0, splitting along feature 0, and then we'll ask a question about feature 1, and we'll try and minimize the Gini. So we'll use a for loop to go along feature 0 and then a for loop along feature 1. And in most cases the data won't be perfectly split, as the simple example showing. So we'll end up with a number of sub-branches, and then we can just have a look at feature 0 and feature 1 of the sub-branches and ask another set of questions using for loops, and then continue along. So you can think of it as a tree with a branch and then a sub-branch and then a sub-branch of the sub-branch, and it will continue until the data is classified sufficiently, and this gives a decision tree. Okay, so let's have a look at on the data again, and now let's have a look at the decision tree estimator. So as it's an estimator, it's going to have a very similar form. So this time the module's tree, and the class is decision tree classifier. And we'll create an instance of it called deck tree. And here we can see the default keyword input arguments. So we can change the estimator within the function cross-validation score, and we can get a new cross-validation mean score. So it's 0.940, which is slightly worse than the other estimators we previously looked at. Now, instead of just using a single decision tree, we can create a so-called random forest, which, as the name suggests, is a series of random decision trees. So instead of just having one estimator, we can have a model of 100 estimators, and each estimator will make a prediction, but the final prediction will be made from a consensus of all the decision trees, so we can think of it as a democracy. So we see when we instantiate the class, the keyword input argument n estimators equals 100 by default. So we've got 100 decision trees. And here we see that the mean score is slightly higher. It's 0.946 opposed to 0.940 for a single tree. So this mean score is still lower than the 0.973 that we got with k nearest neighbours. So let's have a look at another estimator. And let's visually do this. So let's go back to our plot, and I'm just going to increase the line width to 5. And I'm going to reduce the number of data points for clarity. So when we use the decision tree, we asked a question about a single feature. Now instead let's just try and draw a straight line that best separate out the features. So we can put one data point where the mouse is, and then we can put the other data point roughly in a straight line separating out the data points. So we can try something like this. So that would separate the red from the green. Let me get more data points. So instead of every 10 data points, we'll take every 5 data points, which will give us twice as many. Now most of the green data points shown are quite bunched up. Let me take every 4 data points instead of every 5. Okay, so here we see that this line doesn't actually separate all the red data points out that nicely. So let me just try to change the line. Okay, so this straight line is just done very roughly by eye. Now, if we have a look at it in more detail, we'll see that the data points that are closest to the line will pay more significance in actually finding the proper gradient of the line. So these are known as support vectors. And when fitting, we can change the width that we use to encompass the support vectors. So this is shown by the blue line. Now in the actual fitting algorithm, it uses a parameter gamma, and the parameter gamma can be thought of as the inverse of the radius of this blue line. Now we don't actually just need to fit a straight line, we can fit a more complicated curve instead of a line. So we have another parameter called C, which can just be thought of as a measure of the flexibility. So when we use the support vector classifier, we can try different values of gamma and we can try different values of C in order to get the best line to separate out the different classifications. So in order to best separate out the green, the red and the blue in our example problem. Okay, so let's select all the data points, and now what I'm going to do is copy and paste the code I used earlier on to look at creating a k nearest neighbors model of estimators. And we'll instead create a SVC model of SVC estimators. So let's just get rid of the lines of code that we don't need. And now we can instead use the SVC class. So this is in the SVM module, and we'll import SVC and we'll instantiate it. So when we instantiate it, we can see the keyword input arguments. So we've got C and gamma as we discussed before. And we'll leave all the keyword input arguments as their defaults. And we're going to add C and gamma to parameter distributions. So let me just uncomment out the code below. And let's have a look at parameter distributions first. So recall that this is a dictionary. So let me just delete all the key value pairs in it that correspond to the k nearest neighbors. And now I'm going to create a list that corresponds to the powers of C and a list that corresponds to the power of gamma. So let's create C powers equals an empty list, and then within this we're going to have 10 to the power of C for C in numpy.a range. Start equals -5, stop equals 16, step equals 1, and we need to have the d type to be a float here. And let's copy and paste this, and we'll have a list for G powers for gamma. So we'll start at -15 and stop at 3. And now within the dictionary, we'll have the keyword input argument C and assign it to the list C powers, and the keyword input argument gamma, and this will correspond to G powers. So let's change the model name to correspond to SVC and the estimator to be SVC. Let's update the model svc.fit. We want the CV results, the best score, the best parameters, and the best estimator. So let's restart the kernel. And we don't need the predict line, so we can run this code. And the best parameters for C and gamma are the following. And the best score is 0.960. So this is still lower than the best score we've seen for the k-nearest neighbors. Okay, so in most of the visualizations above, we've used PCA to reduce the number of dimensions to 2. So we could see the data in a 2D plot. Now let's reduce the number of dimensions down to 1. And what we're going to do is copy and paste some code from earlier, where we plotted the data in a single dimension, but we used the y value to be the classification. And for convenience, we're only going to have a look at the 0 and 1 data, so we'll only plot the blue and the red data. So let's change this to be x3 and y3. And we'll comment out the green data for just now. Let's restart the kernel. And let's comment out the code from earlier. And now what we want to do is figure out how we can fit some sort of line to this data. So let's try fitting a straight line. So we can do this using the linear model module, and we can import the linear regression class. So we can create an instance of this. And we can fit the x and y data to this. So now what we are wanting to do is just create a continuous prediction along x. So let's create a vector x, which will be the length of the axis. So feature 0, which is the x, will correspond, say, from -3.5 to 2. So we can step in 0.1 and use the numpy.a range function. And then we can predict the values of these x coordinates. And then we can plot this on the plot. So let's plot it as a black line. Let's have a line style that's dotted and have a line width of 5. Okay, so there's a small problem here, and this is because this capital X4 and capital X3 should actually be a lowercase because we've only got one dimension now. So I'll need to use the reshape function to give it -1 rows and 1 column. Okay, so we've got the straight line on the plot. Now, what does the straight line mean? What does a continuous value mean in a classification problem? So it doesn't actually tell us that much because the data point that has a value, a target value of 0.5 doesn't actually mean anything meaningful for us. We've only got classification 1 and 2. So instead of using a straight line, we can perform a logistic regression, and this model is going to have a value of only 0 and 1. So if we go ahead and plot this, and let me also just select only the first 100 data points, so we've only got the classification 0 and the classification 1. Okay, so now if I replot this, we see that we've got this fit, and it's only got the values 0 or 1. And in this case, this line fits the data pretty nicely. So let's add in all the data now, and let's just expand the stop value of X. And I've got an error because I didn't change this to X3 and Y3. So we can see the logistic regression using 0, 1 and 2. And for classification 1 and classification 2, we see that there is some substantial overlay. So we see that there are some green data points that will get misclassified as red, and some red data points that will get misclassified as green. Okay, so the logistic regression is a predictor, and this means it has the method predict proba, so it will predict a probability. So we can calculate y4 predict proba equals log reg, and we can use the method predict proba once again on x4. So we'll get a probability of classification 0, classification 1 and classification 2 for each data point in x4. So what I'll do now is just create a plot with subplots. So in the first subplot, we're just going to plot the original data. And then in the last subplot, we'll plot the result. And in the middle subplot, we'll plot the probabilities. So we can use predict proba, and we want to select the 0th column, and we can make this blue. And we want the first column and the second column, and we can make this red and green respectively. So let's add the shared X label to the bottom, and let's just create a Y label for the other two subplots. So this can be the probability and the estimated classification. And I've got a slight error, and this is because I didn't select all rows alongside the column. So let me just fix that. Okay, so we can see the original data at the top, and we can see the probabilities in the middle plot, and then we can see the estimated classification in the bottom plot. And as expected, we'll see that there's substantial overlap between the red and the green probabilities in the areas where it's hard to distinguish red from green. Okay, so let's now use logistic regression, and let's use it within a tenfold cross-validation, and we'll also have a look at some of the keyword input arguments. So this is going to be a logistic regression classifier predictor class, because it has the method predict proba. So let's import the class from the linear model module. Let's instantiate it. And we've got a keyword input argument C. So we'll create C powers again, but this time we want start equals 0 and stop equals 11. And we also have the keyword input argument solver, and we'll just use the single solver liblinear. And now let's change our model to be a logistic regression model. And update the estimator to be the predictor. Let's restart the kernel and run this code. So I get an error, and this is because I've added parentheses when importing the class. So let's get rid of these. And here we go. We see the best parameters are the following: C equals 10 and liblinear. And we see the best score is 0.94. And we expect some misclassifications just because we could see this when we created the plot of the data. So this performs worse than the k nearest neighbors, so we would stick to the k nearest neighbors for this particular data set. Okay, so just to recap, we looked at the iris example bunch. We converted it into a data frame and saved it as an Excel file. We imported it as an Excel file. We looked at data visualization. We looked at the label encoder, standard scalar, principal component analysis, and Isomap transformer classes. And then we looked at the following classifiers: the k nearest neighbors, the naive Bayes, the decision tree, the random forest, the support vector, and logistic regression. And we had a look at the overview of just using the estimator class, and then the concept of the train test split function, computing evaluation metrics such as the accuracy score and confusion matrix. We looked at the variance of the accuracy score and then performed tenfold cross-validation. And then we performed a grid search and a randomized search in order to save some time. So we demonstrated the above using the inbuilt iris bunch. So recall we imported the function load iris from the datasets module. Now there are other test datasets, and if I just type in load underscore, I'll get a list of just the datasets that we can load. So the next dataset to move on to if you want to practice is the wine dataset. And the features here are some properties of the wine, whereas the target is the quality. The next dataset is the digits, and this is an optical character recognition problem. So the features are each of the pixels, and the target is the actual number that the written character corresponds to. And then after that, there is the breast cancer dataset. And here the features are the properties of a lump on a breast, and it can either be malignant or benign, so cancerous or non-cancerous. And these three classification problems can be approached in precisely the same way as the iris dataset. So basically you want to use the same transformers as before to reduce the number of dimensions, and then perform some plotting so you can visualize the data a bit better. And then you want to use the same estimators as before and find out which one gives the best score for each dataset. And you'll want to use the same procedure as before. Now for the breast cancer dataset, you're going to want to minimize the number of false negatives. So basically people that have cancer which you diagnose and tell them they're fine. It's not really good for a diagnostic test to have a lot of results like this. So for this dataset, instead of just using the accuracy score, you can use the recall score instead. And you should compare the accuracy score and recall score when using tenfold cross validation to select the best estimator.